All right, everyone. Today we're going to be looking at kind of an important concept moving into the last part of the course called surface integrals. Okay, so with surface integrals, we are basically integrating over a three-dimensional surface. And this has several applications, like when we talk about the remaining two major theorems that'll be in the last two videos, Stokes' theorem and the divergence theorem. Right, they involve integrals of surfaces, being able to compute things like flux, right? Also involves being able to use surfaces. And these can be written in a lot of different ways, but essentially this is how they look. So we have the double integral over a surface S of some function, see the notation that they use here. Yep, over some function f of x and y, what are you doing? Okay. And z with respect to some surface S. First off, recurring theme in a lot of the stuff that we've done in this course is being able to rewrite a differential in the appropriate way. So I want us to start by looking at there. Okay. All right. Being able to rewrite differentials in different ways. So ds, I want us to think of as kind of like a change in arc length times a change in area. So like if I have a three-dimensional surface, right? So something that has, say, that kind of a base that has some height to it, right? If I have a three-dimensional surface, this could be S. If you think about it, the part that kind of it's kind of like if I were to shine a light directly on top of that surface on the ground, I would get kind of a picture of this region R that serves as a base. So ds, right, small changes in the surface area along this surface is essentially going to be the product of a small change in area on this region, right? Multiplied by an arc length along the surface. So basically, if you remember your formula from arc length from Cal 2, you had the square root of 1 plus f prime of x squared, and that would be it. Right. In this case, though, we are always going to take the equation that defines the surface, and to evaluate a surface integral, we're going to solve for z in terms of x and y. So basically, we'll rewrite equations to isolate z. This gives us this function g, right? And that's what we're going to differentiate to find this arc length. So if I differentiate with respect to x, I get one thing. Okay, she's getting into stuff. And if I differentiate with respect to y, I get another thing. So we're able to rewrite this in terms of a differential that we have worked with extensively, right? This is like the differential defined areas of two-dimensional surfaces or volumes, right? By integrating a function in terms of x and y. Okay, Kat, come on. What are you doing? No, no. Oh, curious, curious, curious. All right. All right. So anyway, this is how we rewrite the differential ds. And then essentially the entire surface integral gets rewritten as the double integral over some region R, which is based off of, like I said, the shadow that you would get if you shine a light directly on top of the surface. So double integral over the two-dimensional region R of gxy times this arc length piece dA. Right, so with all of these surface integrals, it's kind of the same thing. And from all the things that we've learned, in particularly this leg of the course, we even have different ways to express this, right? So in the last section, we learned how to write parametric equations for surfaces. We can use those as well to evaluate surface integrals. But we'll start off with a simple case where we just do a surface integral over a surface using these definitions that I've laid out. Okay. So our first, oh, whoops, should actually be F, not G. All right, the thing about that though is that Z is going to be rewritten in terms of X and Y. All right, so this G does factor in, it's just there. All right, so looking at our first example, let's say that we want to evaluate a surface integral, integrate over a surface S. The function that we're integrating is y squared plus 2yz ds. And the description of the surface that we're given is that S is part of a plane. So it is the part of the plane given by 2x plus y plus 2z equals 6 that lies in the first octant. Right. So this puts a couple of restraints on x, y, and z. If we're in the first octant, then x, y, and z are all going to be greater than or equal to 0. All right. But to begin with, we're going to look at the surface S. This is the equation that we're going to use to basically isolate Z to set up what we're going to do for our differential. So if I isolate this and I solve for Z, I get 2x plus y. Blah, 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 blah. Right, I'm going to end up getting Z is equal to 6 minus 2x minus y, all divided by 2, right? Which you can also write as 3 minus x minus 1/2 y. So now that I have Z isolated, I can set up I can set up this g of x, find its partial derivatives to figure out my differential. So we know that ds is going to be equal to the square root of 1 plus the derivative of z with respect to x squared. And if I write that out to the side, the partial of z with respect to x is -1. Also going to need the partial of z with respect to y. It's going to be -1/2. All right. So 1 plus partial with respect to x squared plus partial with respect to y squared dA. Right, and I'm still sticking to dA because I don't know what order I want to write the x and the y in yet. Right, I would need to set my bounds for my integrand or my integral before I can do that. So we're gonna just go with this one. So if I simplify, this is 1 plus 1, that's 2 plus 1/4 gives me the square root of 9/4. Right? If I take the square root of that, I get 3/2 dA. So when I rewrite my surface integral, I know that double integral over the surface of fxyz ds is going to be equal to the double integral over the region R. And now that I've written R, I should stick to just x's and y's, meaning I need to replace this z with what I got from solving for z with the surface. So I would write y squared plus 2y, and then in place of the z, I'm going to put in 6 minus 2x minus y all over 2. And then I can replace the ds with 3 halves dA. So we've essentially converted at this point our surface integral into a two-dimensional, basically double integral over the region R. Now, if I were to simplify a little more, I know I could pull the 3 halves out. I know if I multiply by 2, this goes away. I could set my bounds up, but I'm going to hold on that. Okay. And then my integrand, I get y squared plus 6y minus 2xy minus y squared dA. And you'll notice that the y squareds are going to subtract out. And also notice that these coefficients are both even, meaning that I can factor a 2 out from my integral. So if I multiply that 2 that I'm factoring out times 3 halves, I'm left with just 3 double integral over the region R. If I factored that 2 out, I'm going to leave behind 3y minus xy dA. All right, so now that I have everything pretty simple, I can think about my bounds. So thinking about the bounds, remember, we're sticking to the first octant. That means that x, y, and z are all going to be greater than 0. All right, so one thing I can do is I can take what I got from isolating z. That was 3 minus x minus 1/2 y, and set this greater than 0 or equal to 0. And I have two options. I can either isolate y in this inequality, or I can isolate x in this inequality. Computationally, I think it would be easier to isolate the y, so that's what I'm going to do. If I add 1/2 y to both sides, I get 1/2 y is less than or equal to 3 minus x. If I multiply both sides of my inequality by positive 2, I get y is less than or equal to 2 times 3 minus x. That means that whatever my value of y is, it has to be less than 2 times 3 minus x. Right, and I know that because I'm sticking to the first octant, that the y coordinate also has to be greater than 0. Meaning that I can let my inner bounds be from 0 to 2 times 3 minus x. By choosing that, I've basically made it so that, go ahead and write this out. I've basically made it so that I have to integrate with respect to y first. Remember, if one of my bounds is in terms of x, then my differential cannot be dx. All right. Now I have to figure out what the possible values of x are. Again, because I know that we're going to stay in the first octant, I know that x has to be greater than 0. But in order for this quantity to remain positive, right, I know that x has to be less than or equal to 3. So my bound for x will be 3. Right? Because if I go above 3, then this becomes a negative quantity. So that's how I figure out the bounds for x. All right, so now I've got an iterated integral that I can easily evaluate to find the value of my surface integral. So doing a little bit of third grade math, we're going to take the integral of this with respect to y. So that's going to give me 3 halves y squared minus x halves y squared. We're going to evaluate that from y equals 0 to y equals 2 times 3 minus x, and then integrate with respect to x. So when I plug this 2 in, keep in mind that this quantity is going to be squared in both terms. So that means both the 2 and the 3 minus x are going to be squared. So what I can do is I know that I'm going to multiply these coefficients by 4, right? Because that's 2 squared, which will end up giving me 6 for this coefficient and 2 for this coefficient. Right, so again, I can factor another 2 out. So I get 6 times the integral from 0 to 3 of 3 times 3 minus x squared minus x times 3 minus x squared dx. And now you might look at this and notice that this is actually factorable as well, because both of the terms in my integrand have a factor of 3 minus x squared. I can actually rewrite this entire integrand as 6 times the integral from 0 to 3 of 3 minus x to the third dx. So at that point, you could do a pretty simple u substitution where you let the u be 3 minus x, so you end up getting a negative in the mix. Yeah. So doing that, I would end up getting negative 6 over 4. That's going to reduce to 3 over 2 times 3 minus x raised to the power 4, evaluated from x equals 0 to x equals 3. So if I plug 3 in, I know I'm going to end up getting 0. 3 minus 3 is 0. Minus a negative, so plus 3 halves times 3 to the 4. And if I evaluate that, I know 3 to the 4 is 81. Multiplied by 3, I get 243 over 2. And that is my answer. Lots of algebra in that one. All right, if we look at the next example, exercise to the reader. For example 2, you can go back over. It's the exact same thing. The only difference is that the integral is a little bit more, I don't even want to say challenging. It's just a reminder of what the derivative of arc sine looks like. Yeah. So I'm going to go to the next one where we actually find the mass of a surface laminate. So remember when we were talking about mass a while back in chapter 14, I think, we were talking about laminates being these flat two-dimensional objects that have varying surface or varying mass density. We can actually expand this to a flat three-dimensional object. And when I say flat, I mean that you can kind of just pinch a part of the surface at any point, right? So we're going to look at a cone-shaped lamina this time. So we have the cone-shaped lamina, is given to us by the equation z equals 4 minus 2 times the square root of x squared plus y squared. And we have the restriction that z is going to be between 0 and 4. Which, if you remember that this is the equation of a cone, and since the negative is in front of the x and y part, we're going to open downward, which means that 4 has to be the top of the cone. You don't necessarily need that explicitly written out. But anyway, we know that that's the surface. We are given that the density is proportional to the distance between point and the z-axis. Okay, and we want to find the mass. Yep. We want to find the mass of the cone-shaped lamina. So with this one, kind of a lot going on there. But remember, how do I find mass? I take the integral of the mass density. Back earlier when we talked about mass and moments and all of that stuff, we kind of confined it to these two-dimensional regions, right? So the integrals that we used were just double integrals over region R. Now, because we want to find the mass of a three-dimensional lamina, right, we still want to integrate the density, but this time instead of taking a integral over region R, we're taking the integral over a surface S. And the integrand is going to be our density. I could put a Z there, but if you were to actually write out the density, it wouldn't even depend on Z. All right, but anyway, so essentially this is going to tell us, this surface integral is going to tell us what the mass of that cone-shaped lamina is. So I have a couple of things I need to do. First off, we're lucky that Z is already isolated for us, so we don't need to do anything with regard to that. This is already our G of xy that we're going to differentiate to rewrite the differential ds. Unfortunately, though, the derivative that we have to take here is a little bit more involved than what we did in the last example, right? To remind you, though, whenever you have a square root, you can always write the root as a power. Square root we can rewrite as the power 1/2. So when I go to find my partial derivatives, okay, I know the derivative with respect to anything of 4 is going to be 0. Okay, so I really only have to worry about this minus 2 times that. Since x is inside the root, we have to use the chain rule to get this partial derivative. So we're going to bring the 1/2 down, multiplies the minus 2. Should probably go ahead and write the minus there. And the 4, why not? All right, there we go. So I can bring the 1/2 down. Multiplying by that 2, we're going to just get -1 times the inside. Remember, with chain rule, you don't change the inside, right? But you do take 1 away from the power and you multiply by the derivative of the inside. Since we're taking the derivative with respect to x, derivative of y squared will be 0, and derivative of x squared will be 2x. So if I write this out in square root form, I end up getting -2x over the square root of x squared plus y squared. And you might be thinking, Professor Dan, shouldn't we be using polar coordinates because that's an R? Yeah, actually, we are going to use polar coordinates. But not until we've rewritten this as an integral over a region R. Right, so after we've done all of the replacements, then we'll convert to polar coordinates. Right, but for now, we're just sticking it out and doing the algebra. Okay, so we're going to need partial derivative with respect to y now, and it's going to be the same story. That's going to be 0. I'm going to have to do my chain rule with this one. So bring the 1/2 down, that becomes -1. Leave the inside exactly the same because you never change the inside with chain rule. Take 1 away from the power, which taking 1 away from 1/2, that's -1/2. Multiply by the derivative with respect to y this time of the inside. Get 2y. And then if I rewrite this one in root form, I end up getting -2y over the square root of x squared plus y squared. And at this point, since I have these partial derivatives, I can go ahead and rewrite my differential. So ds can be rewritten as the square root of 1 plus my partial with respect to x squared. So we're going to take this whole thing and square, plus the partial with respect to y, also squared. dA. So at this point, simplification is our friend. This is actually going to simplify to something that's really nice and easy to deal with. So if I go ahead and square these guys, I know that we're already going to have the same denominator because they both have the same denominator. So I know we're going to be over x squared plus y squared, right? The square root went away because I squared each of them. Then when I square -2x, I get 4x squared. When I square -2y, I get 4y squared. I can factor 4 out. And when I factor that 4 out, my numerator is now the same as my denominator, which is pretty convenient because now I can just say that this is 1 and that my differential is the square root of 1 plus 4 dA, so the square root of 5 dA. So that turned out pretty nicely. So the next thing, now that I've figured out how to rewrite dA, I should probably go back and figure out what this density function is because that's what I'm going to have to integrate in this surface integral. So it tells us in words that the density is proportional to the distance between the point and the x-axis. And if our shape is a cone, try to make the best cone that I can. And it's a little off center. All right, but anyway, if my surface is a cone, right, and this marked point here is the origin, if I pick any point that's on the cone, the distance directly from what's it called? From that point to the z-axis is just the square root of x squared plus y squared. Right? Because the distance from this to the z-axis doesn't depend on z. Right? It's like looking at the distance from a point that's on a circle to the center of that circle, right? Finding a radius. And you know what? Radius is the square root of x squared plus y squared. So we know that we're proportional to, meaning equal to a constant times the square root of x squared plus y squared. Okay. So now that we know what our density is, and we've figured out how to rewrite our differential, we can look at rewriting the entire surface integral. So we know that this is going to be equal to, I'm going to take the constant k out. I'm going to take the square root of 5 from my rewrite of the ds out. Just be careful to end your square root before it starts to go over the k. Then we're going to take a double integral, and at this point, I can actually let me write this. X squared plus y squared a, this is over region R. All right. So at this point, I can actually do that conversion that I mentioned earlier, where we go into polar coordinates to evaluate this integral. So first thing, how do I rewrite the integrand? We know that the square root of x squared plus y squared is also known as r. So I know that my integrand is going to be r. How do I rewrite dA if I'm in polar coordinates? R dr d theta. So multiply by the r that's already there, we'll get r squared dr d theta. Okay. Now, if I were to think about the bounds that I'm going to need, what are the values for my radius? I know that z ranges from 0 to 4, right? Which means that the lowest possible value of r would be 0, right? Because if I set z equal to 4 and solve for r, I get 0. If I set z equal to 0 and solve for r, I end up getting 2. So my radius is going to range from 0 to 2. And then my theta, because I'm going all the way around, I'm not just doing a piece of the cone, I'm doing the whole cone. I know that my theta is going to range from 0 to 2 pi. So now I've rewritten my surface integral as an iterated integral in polar coordinates. And from there, we're just doing the integral. Third grade math, we got it. Square root of 5k times the integral from 0 to 2 pi, then evaluate the inside. We know the antiderivative is going to be 1/3, so I'm going to pull the over 3 out, r to the third, and we're going to evaluate from r equals 0 to r equals 2, and then integrate with respect to theta. So I have the square root of 5 times k divided by 3, integral from 0 to 2 pi. And now if I evaluate at these endpoints, 2 cubed, I get 8, 0 cubed, I get 0. So now my integrand is just 8, which means that my mass is going to be 16 pi times the square root of 5 times k all over 3. All right, that's going to be 8 theta, plug 2 pi and you get 16 pi, plug 0 and you get 0. So that is the mass of the three-dimensional lamina. Pretty fun stuff. Okay. Now for the next one, we're actually going to go back and look at basically the one that we, remember if this is the one that we did or the one that we skipped, right? But we're going to go back and look at a surface integral that we can evaluate using parametric equations, right? Because what good is it going over parameterizing surfaces if we don't get to actually use it? And it actually is pretty important because at the end of the video, we're going to talk about flux and how to compute that, and that involves a lot of vector stuff. So it's good that we're doing this one. Now, for this example, right, the surface integral we want to find is double integral over the surface S of x plus z ds. And the surface S, right, is the piece of a cylinder. So the part of the cylinder given by y squared plus z squared equals 9 that's in the first octant. So again, if you're in your first octant, that means that x, y, and z all have to be greater than or equal to 0. All right, and specifically, we're also given a constraint that x has to be between 0 and 4, which is a necessary thing to be told because otherwise that cylinder will go infinitely in all directions. And then that would mean that we'd have to evaluate an improper integral. All right, but anyway, getting back to this. That's our surface. That's the surface integral that we want to compute. And we have all of the different restrictions that we're going to need. So first off, I want to start with my surface. Remember, you're always starting with your surface to solve for z. Right? I end up getting that z squared is equal to 9 minus y squared. If I take the square root of both sides, I get z is equal to plus or minus the square root of 9 minus y squared. Thing is, I'm not going to actually use the negative root because we are confined to the first octant, which again, remember, means that x, y, and z are all positive, or at least non-negative. All right, so now that I've solved for z, I can get my partial derivatives, right? Partial with respect to x is pretty easy. There's no x anywhere in that, so that's 0. Partial with respect to y, I have to use my chain rule. So remember, this can always be written as 9 minus y squared to the power 1/2, because it's a square root. If I take the derivative with respect to y, chain rule, I bring the 1/2 down. I don't change the inside, I never change the inside. I take one away from the power, and then I multiply by the derivative with respect to y, which would be negative 2y. All right, multiplying that 1/2 times the 2 will leave behind a 1. And this is going to become negative y over the square root of 9 minus y squared. All right, and again, over negative exponent goes to the bottom. Square root 1/2 power is the same as square root. So now that we have our partial derivatives, we can rewrite ds. Oh, wait, why are we doing it that way? Ah, silly. Yeah, whoops, my bad. Yeah, I'm doing that the old way, guys. That is correct, but that's not how I wanted to do that example. So what I did want to do is actually parameterize the cylinder first. Okay. Meaning that I come up with a set of parametric equations. So first off, we can write our parametric equations as a vector valued function using two parameters u and v. Okay. First thing is that the cylinder, if you pay attention to the equation of the cylinder, the x part is going to be the height of the cylinder, right? The circular parts are going to be in the YZ plane or parallel to the YZ plane. So when I go to write my x component, it's literally just going to be u, the parameter u, or the parameter v as long as you're consistent and switch to the other one for the other stuff. All right, but don't make it complicated, just do u. All right, now I mentioned in the YZ plane or parallel to the YZ plane, we have a circle with a radius of 3, right? So circle centered at the origin, radius of 3. That means that my y and my z coordinates, or my y and my z components, are going to be 3 cosine of v for the j component, right? 3 is the radius, cosine of v because in the YZ plane, y serves as the horizontal axis, plus 3 sine of v for the z component. So this is a set of parametric equations that I have to, yeah. that I can use to evaluate this surface integral. Now, the thing that's different about this approach is that to rewrite our differential ds, rather than using the square root of 1 plus g x squared plus gy squared dA, right? We actually use the magnitude of, you guessed it, the normal vector. To remind you, the normal vector is what we get from taking the cross product of the partial derivatives with respect to each of the parameters, right? So first I'm going to take my partial derivatives with respect to each of these parameters. So partial derivative of r with respect to u, right? For my x component, derivative of u would be 1, so I. For my y and z components, though, there's not a u anywhere in those components. So both of those will have a component of 0. So ru is just I. If I take the partial with respect to v of r, there's not going to be an I component. There's no v in this component at all. But for the other two, I'm going to get -3 sine of v for my j component and +3 cosine of v for my k component. All right, and now that I have these partial derivatives, I can determine my cross product. So my normal vector is going to be the cross product of the partial with respect to u cross the partial with respect to v. So remember, with your cross products, the order matters, right? And we're basically taking the determinant first row of a 3x3 matrix. First row is our unit vectors. Second row, we have the first partial derivative. So 1, 0, 0. That's going to make things pretty easy. And then bottom row, we're going to have our partial with respect to v. So 0 for the I component, -3 sine v for the j, +3 cosine v for the k. Now to find this determinant, remember we can split into 2x2s. So if I cover up first row, first column, and I take the determinant of that matrix, I get 0. Minus j. Then I cover up first row, second column, and I take the determinant of this part. So that's going to be 1 times 3 cosine v minus 0. So just 3 cosine v. And then for the k component, cover up first row, third column, and you take the determinant of what's left over. That's going to be -3 sine v minus 0. So my normal vector ends up being -3 cosine v j minus 3 sine v k. And to rewrite my differential ds, I'm going to need to find the magnitude of this normal vector, which remember is just the square root of the sum of each component squared. So 0 squared gives me 0. If I square -3 cosine v, I get 9 cosine squared v. If I square -3 sine v, I get +9 sine squared v. We know we can factor a 9 out from that. And if you factor a 9, what are you left with? Cosine squared v plus sine squared v, which is 1. So 9 times 1, we get 9. Square root of that, we get 3. Pretty easy. So rewriting that differential ds, we know the magnitude of our normal vector was 3. So we can rewrite ds as 3 dA. And now that we've figured that part out, basically we can go back to our surface integral. and take our integral in terms of the parameters that we use to rewrite the surface. So for this one, we know that x had to be between 0 and 4, which means that the parameter u has to be between 0 and 4. Then for y and z, right, we're basically only sticking to the first octant. If you were to draw that surface out, you would basically get a quarter of a cylinder. Right, so that's your YZ plane, that is your X plane. All right, so we only get a quarter of the cylinder. That means that the angle that we go around, right, which would be V, would only go from 0 to pi over 2 because we're only sticking to the first octant. So I can do it in any order I want. I can start with X, I know, or well, U. I know that U goes from 0 to 4. And then theta I know goes from 0 to pi over 2. 0 less than or equal to V less than or equal to pi over 2. Why do I call it theta? Because it's an angle, and that's what we usually call angles. Yeah. All right. So now that I have the bounds, I know that I can rewrite my integrand using the parameters that we got. So x, remember, was equal to u. It's the x component. Z, remember, was equal to 3 sine of b. And because of how I wrote my bounds, I'm going to do my integral with respect to u first, then v. Right? And realistically, you could have done it either order as long as your bounds match up. And then, of course, there's going to be a 3 because of that magnitude. All right. So now that we've got that, take the integral from 0 to pi halves. My antiderivative with respect to u is going to be u squared over 2. Since the second term doesn't involve u at all, I know the antiderivative will be 3u sine of v, or 3 sine of v times u. And we're going to evaluate that from u equals 0 to u equals 4, and then integrate with respect to v. So if I plug 4 in for u, I get 16 over 2, that's 8, minus 0 leaves me still with 8. Now for this one, if I plug 4 in for u, I get 12 sine v. If I plug in 0 for u, I get 0. So plus 12 sine v. And we'll integrate that with respect to, not theta, v. All right. So at this point, I also notice that both of my coefficients are multiples of 4. So if I want to make it so that I'm dealing with smaller numbers, I can factor a 4 out. Multiplied by that 3 will leave 12 in the front. If I factor a 4 out, I'm leaving behind a 2 for the first term and 3 sine v for the second term. All right, and now I take my integral with respect to v. So I get 12 multiplied by 2v. Antiderivative of sine is negative cosine. So minus 3 cosine v. Evaluated from v equals 0 to v equals pi over 2. So looking at the first term, if I plug pi over 2 in, I get pi. If I plug 0 in, I get 0. So we get 12 on the outside, pi. Now let's look at the second term. If I plug pi over 2 in, I get 0. So minus 3 times 0 minus, and then if I plug 0 in, I get 1. So I end up getting 12 times pi plus 3. And that's the answer. So we were able to do a surface integral using parametric equations that we wrote for the surface, right? Which is a fun little thing. And the reason that it's important is because the stuff I'm going to talk about in the next couple examples involves sort of a directionality or an orientation of the surface. So let's see, what is the next example? Oh, actually, I'm only going to do one more example. It's nice. Yeah. So before I get into the example, just a little kind of conceptual talk about this word. So when we talk about flux, flux is essentially the rate that something flows through a surface, right? So this is a commonly encountered concept if you ever study something like fluid mechanics, fluid dynamics, right? Because if a fluid, like a gas or a solid, goes through a surface, right, you want to know the rate at which you move through that surface, right? Because whatever's passing through that surface may, for example, be undergoing some kind of a purification process, kind of like cleaning up water, right? Um, or really anything. So flux tells us the rate at which something passes through a surface. With that said, it's important for us to know the direction that the surface is oriented, which is why we use the normal vector. Because if I have a surface, remember the point that is normal to that surface say that's our surface. And we're kind of looking up the surface there. But if I have a point on the surface, right, the vector that's normal to the surface at that point actually gives me the direction of the flux, right? The direction of the flow that we're going. All right. So when we compute the flux, we're actually just integrating. So write this out. Flux, we're actually just doing an integral over a surface, right? So integral over the surface S of F dot N ds. Okay, and here N represents our normal vector or something related to it, and F represents the force that's acting on whatever's flowing through the surface, right? So for example, if you have ever had to replace pipes, like for a plumbing system, which I have, and man, that was a lot of work. Um, Gravity acts on the fluids that go through those pipes, right? So the vector normal to the surface that makes up the pipe in that case, right, would indicate um, yeah, would indicate the direction of the flow under this force. Right, and calculating this integral gives us the rate at which, again, something passes through the surface. So pipes and plumbing really aren't the best example of that, but yeah. The point is that that force can be a lot of things. It can be gravity, gravitational force. It can be an electric field, right? So like if you've taken E&M or just like physics, I think second semester, you have like these spheres and you have charge flowing through the spheres, right? You can actually compute the flux by evaluating surface integral, specifically this surface integral. And your textbook gives a nice, neat little concise way of rewriting these integrals. Present that here for you. So the flux, otherwise known as the surface integral, integral over the surface S of force dot normal vector ds is equal to the integral over a region R of the force F dot, and then it gives a nice little vector form here. Negative gxi minus GYJ plus K dA. This is one way to write it, specifically if you are looking at at a surface that's oriented upward. So there's a difference between surfaces that are oriented upward and surfaces that are oriented downward, right? That's something that's usually going to be, or usually that is going to be kind of given to you in the problem, right? And really the only difference between upward and downward is a sign. Yeah. So this is upward. If you have a downward oriented surface, then your flux is defined by this surface integral, same thing. The only difference is that the vector whose dot product, or who we're dotting with the force, is the negative of what we did there. Wait, what did I write? Dude. Yeah, mixing notations there. So we get positive gx I plus gy j minus k, and not pointy brackets because we're using unit vectors, dA. Okay. And again, this gx gy is the same thing that we looked at earlier, where we take our surface, right? So the equation that models the surface, we isolate z and then take partial derivatives. That's how we get these components. So let's look at an example. So let's say that we have a paraboloid S that is defined by z equals 4 minus x squared minus y squared. All right, and to remind you, this is going to be a paraboloid that opens downward, centered at, or basically the level curves are all centered at the origin, and the maximum height or z coordinate is 4. If I were to draw that out, that's 4, top of the paraboloid, comes down, draw a little circle there. There we go. All right, so that's our surface S. And lucky for us, it's already written in a way where z is isolated, so we don't have to solve for z like we have in a couple of these examples. What other stuff are we told? All right, we're told that the paraboloid is oriented upward, which we can also see from the graph that we drew, which means that we're using this formula for the flux, right? Yeah, and then we're also told that the force that's acting on oh, yeah, we're doing a mass then. So we're told that the force that's acting on the object is given to us by xi plus yj plus zk. All right, and we're also told that there's a mass density rho, right? And this is a special kind of flux question. Yep. Specifically, it's asking us to find the rate of mass flow through the surface S. Yep, that's it. Yep. So that's what we're given. This is a question that we're answering with this. So rate of mass flow really just means that we're multiplying this vector F by the mass density. And double check. Yeah. Very important. Yep. Specifically, we have a uniform mass density. So with that said, the rate at which we flow through S. That verbiage is the giveaway that I'm trying to find the flux. Okay. Now that I know that I'm finding the flux and I know that my surface is oriented upward, I can set my integral up. I know that this will be the double integral of f dot n ds, all right, which I can rewrite as the double integral over region R of the force, which remember, because of this mass density component, is going to be rho, a constant, times the vector f, which remember would just multiply each of the components by rho. So it's kind of like saying rho xi plus rho yj plus rho zk. Rho zk. Anyway, so we're taking the dot product of that with negative gxi minus gyj plus k. All right, but before I can set that up, I do need to get my partial derivatives. All right, so my partial of z with respect to x is going to be negative 2x. The other terms don't involve x, so their derivatives are 0. Partial of z with respect to y will give me negative 2y. So the dot product that I'm taking is my force field dot negative, and then my partial with respect to x, I, minus, then my partial with respect to y, j, plus k, dA. So next, a little bit of simplifying before I throw some bounds on this. First off, rho is a constant. I can pull it out. F, to make my life a little easier, I'll write in component form. It's just x, y, z. Then this vector I can also write in component form, positive 2x, positive 2y, 1. So now taking the dot product, first times first, I get 2x squared. Second times second, I get 2y squared. And third times third, I get z. Remember, you add them together, and that's the dot product. So now that we've taken the dot product, we have our integrand in terms of just x, y, and z. We can set the rest of the integral up. Right, so we can look at the region R and figure out how we're going to write dA. So for this one, we could basically write this integral out in, well, actually, we need to take care of that z first. Yeah. So we need to take care of that z first. Then we could write our integral in polar coordinates. So with z, remember, just like in the other integrals, we've done this with the other examples as well. When I have a z in my integrand, I can rewrite it with whatever I got from isolating z in my surface. So I get 2x squared plus 2y squared, and then instead of z, we're going to write 4 minus x squared minus y squared. Okay, I got dA. Now, if I combine like terms, I have rho double integral over the region R. Now I'm only going to have one of each of these. All right, so we have x squared plus y squared plus 4 dA. And at this point, we actually have a couple of options. What your textbook does is it takes this and writes it out in polar coordinates, which is definitely a thing we can do. We also could stick to rectangular for this because taking the integral of x squared and y squared is not really difficult, right? Um, the only thing to remember, though, is that if you do decide to put this in terms of polar coordinates, that you replace your dA correctly. Remember, it's not just dr d theta, it's r dr d theta. And then when you go to write your bounds, that's another thing you have to keep in mind. If we were to stick with rectangular coordinates, though, we would need to basically write an equation for each of the circular cross sections that I could take of this paraboloid, right? So we know that the y coordinate is related to the x coordinate through the equation of a circle, right? So y would be the square root of the radius minus x squared. So staying in rectangular coordinates, while the anti-differentiation part isn't really that hard, setting up the bounds would be a little more difficult. So I would say to follow our intuition, we go to polar coordinates, right? Because the setup for the bounds will be a lot more intuitive that way. So we still have rho. I'm going to put bounds on these, but I do need to replace everything in terms of polar coordinates. So x squared plus y squared can be replaced with r squared. dA, remember, is replaced with r dr d theta, not just dr d theta. And then if I choose to use this order of my differentials, I have to start with the values of r first. So I know that r goes from 0 to, in this case, 4. Because the region, yeah, actually not 4, 2. Yeah. Because the region that we are looking at, the surface, is also specified to be above the xy plane, right? So that would imply that the z has to be greater than 0, which means that 4 minus r would have to be greater than 0. Or, well, 4 minus r squared would have to be greater than 0. That means that r has to be between 0 and 2. And if we choose 0 to 2, then the angle will be 0 to 2 pi. From there, we're just taking an integral that is fairly straightforward to evaluate. So we end up with, hope my computer didn't die. Rho times the integral from 0 to 2 pi. If I distribute that r, that would be r cubed. Antiderivative would be r to the 4 over 4. Distribute the r, I get 4r. Antiderivative would be 4r squared over 2, which would just be 2r squared. We evaluate from r equals 0 to r equals 2, and then integrate with respect to theta. So I get rho multiplied by 0 to 2, or integral from 0 to 2 pi. That's going to be 16 over 4, so 4 plus 8. If I plug 0 in, I get 0. So my answer would end up being 24 pi times the constant mass density rho. And that's the flux. That is the rate of flow of the mass through the surface S. So with that said, we did cover quite a bit of ground today. So with surface integrals, you are starting off by looking at your surface, isolating z if it's not already isolated. Then you take partial derivatives of whatever z is equal to and use that to rewrite ds, right? So ds is equal to the square root of 1 plus partial with respect to x squared plus partial with respect to y squared dA. And from there, you kind of just look at it the same way that you've looked at these other problems where you're setting up iterated integrals. It's just the same thing over and over again. We also talked about how you can use parameterized surfaces, so parametric equations to evaluate this. The only difference is rather than doing that setup where you solve for z and then take partials and all that, you find the normal vector. So RU cross RV, find the magnitude, and that's how you get the new differential, right? Magnitude dA. Um, we also learned about flux, which is defined as I've written it here. Um, you have different formulas for upward versus downward oriented surfaces. And then we did an example involving flux. All the same principles applied, right? After you take the dot product, you still have to replace the z. If you want to write in polar, you can write in polar. If you want to stick to rectangular, you can stick to rectangular. Just be wary about the dA for polar. Don't forget that extra R. It will screw you up if you don't remember it. Right. So that's about it for this portion. Happy mathing.